All right. Good evening, everyone. I hope you guys are doing well. How is the weather at your side? Hope you're not catching cold too much. Uh, this class is quite very interesting, very simple. I do not expect anybody to have uh, any issue at all because it's quite very simple. But I would implore everyone to please try and pay real attention because, as simple as it is, once you get the technology, you can never go wrong. It's very simple. Test for independence. We're still on chi-square. We started chi-square some times back, and we have spoken on goodness of fit. I told you guys that we have two major categories while doing conducting a chi-square test. We have the goodness of fit, and we have the test for independence, test of independence. Now, this is all under chi-square, all right? And we have, I will just explain to you the technique because it still has a similarity to goodness of fit. The difference is hinging on how to get the expected value, all right? Now, I believe you guys should have really understood goodness of fit. I told you guys that just as the word implies the phrase, how good does what you observed actually did fit what you were expecting. So on that goodness of fit, you had an expectation, all right? And then you went on to carry out an observation. Then what you want to really test for is, did they fit? Was there like any fitting between the observed and the expected? So it's just always very simple. All you need to do is follow the procedures I explained. Now, that of test for independence is literally very similar also. We have just a little change, and which will really be that of the expected. So you guys should recollect that I told you that the test statistics for chi-square is this. I believe by now everybody should be familiar with this. This is the test statistics for a chi-square distribution, all right? And when we're dealing with goodness of fit, we always add the expected. Sometimes, if you remember what I told you, sometimes you get your values in percentages, you have to convert it, and so on and so forth. That was in our last class. For test for independence, the major thing that I want to stress on is how to get your expected value. That's the elephant in the room, which you have to take care of adequately. All right. Now, but before I go into the technique on solving that, I need to tell you how to really state the hypothesis. Because as I told you guys already, if you do not state the hypothesis right, it's almost as good as not running the right test. Because if you went on to say your hypothesis was something when it wasn't supposed to be like that, let's say you said your null hypothesis was, if for instance you said your null hypothesis was something, and let's say that was wrong. Of course, if you end up saying you rejected that when you're supposed to accept that, so if at the end of the day your conclusion was I rejected H naught, now let's assume you went on to flip what was supposed to be in HA. You fix it on HO. So what you were supposed to say in HO, you were saying in HA. What you were supposed to say in HA, you are saying in HO. Obviously, there's going to be an issue there because if you go on to conclude that you rejected H naught, that means the null hypothesis. That means you would be rejecting what you were supposed to accept. So that's the reason why stating your hypothesis is quite very key. It's a skill you have to know, and it's quite very simple. I told you that under goodness of fit, you state your hypothesis by making sure your null hypothesis echoes the word that says your observed value did fit your expected value. So in that case, you are going to be saying in your HO all the time. Of course, I told you may use a different wordings. We may have different wordings. Every one of us may even probably have not the exact word being written in our null hypothesis, but they must be referring to the same thing. It must be in the same context of saying this did fit this. That's what our HO, under goodness of it, should always say. Like, I believe we did a question where we had issues around days of the week, expected absences, and then observed absences in a school. So now we need to say that the frequency we got when we observed the absences did fit that of what was expected. So that means we could say things like equal frequencies in the HO. That means there was fitting between the observed frequencies and the expected frequencies. Then, of course, your alternative hypothesis will say the opposite of that. That means they did not fit on equal frequency. All right. One other way, if you recollect, we stated hypothesis under goodness of it is saying things like saying the owner distribution is correct. That means what the owner wrote and expected was actually the case. It's this fit, but the alternative will be say the owner distribution was not correct. What he was actually expecting is not actually what happened. The observation did not fit the expected. So always note this thing so that you never go wrong. Now, for test for independence, this is how you state your null hypothesis. Test for independence, the HO, that means the null hypothesis, must always have the context of saying there is independence. That means there is independence. Make sure there is like that statement in your HO that must reflect that independence existed. All right. So that's how so your HO must say so your HO says there is independence. Your HA, your alternative hypothesis, will say there's no independence. That must be the context. Now, it may not be in exactly these words, but it must be framed to mean this. All right. Depending on the context of your question, that's how you want to be framing more of the null and alternative hypothesis. So independence is the general thing it should say, but of course, depending on the question you're dealing with, you may want to use the context of the question to reflect in your HO. You see an example quickly. So as I said already, more of what we'll be doing here is just to try to clarify how to find the expected value. And after that, we'll go on to solve a few questions, and that'll be all. It's quite very simple, no so much to hit. So I'm going to be giving you a table right here. This table is going to be representing different herbs and their effect. Probably they make what's the cost or the effect of herbs on a sick person So this is the table right here. So you can see now abs the first ab 1, 20 people. If a sick person used, ab 1 was used, there was still this 20 was still sick, whereas 100 not sick. App 2 was used. We have 30 sick, 110 not sick. When you make use of placebo, 30, 90 not sick. Now, good. Before I go on to explaining what I want to explain, I want you guys to recognize something I already hinted to you guys before. One of the way we call this table, we call this table contingency table. If you hear the word contingency table, this is an example of what we call a contingency table. And there are different words that are often used when dealing with tests for independence. You see, you can see the word contingency table, which is the most it's the most, do I say statistical name being given to this? Sometimes we talk about cross classification. Cross classification. Sometimes we may say cross tabulation. Sometimes some people may just say cross tab. And these are some of the names they refer to. Some other people will say two-way table. Two-way table. Now, all this is all. Okay, it looks like some people are talking about it being blurred. Is it better? What do you say now? Is it better, right? So all these are different nomenclatures you can give to a table like this. Of course, I said contingency table is the most statistical name you may want to use. Now, what does all this mean? You can see the names being given: contingency table, cross classification, cross tabulation, cross tab, two-way table. It's obvious. It's obvious. It's obvious. You can see that this table, cross tabulation, you have, this is two columns right here, and two rows and three columns. So when you have something being tabulated against something, this 20 right here doesn't stand for just AB1 alone. You cannot just look at 20 as representative of AB1. No, 20 represents AB1 and sick. 100 represents AB1 and not sick. 30 represents AB2 and sick. So that's the way you read a table like this. All right. Can you please give me a signal if you can still hear me? If you're still following me, please. Can you guys can anybody just give me a signal to confirm that the complaint being said is just at probably their hand, not everyone is having the same issue? Can anybody confirm to me that you can hear what I'm saying? Okay, good. All right, thank you. So okay, is it blur, or is it just probably okay? You can see. Okay, it's all right. Now, 30 here represents placebo and sick. Now, placebo is that thing medical practitioners sometimes do give to patients that actually do nothing. They're just more like a psychological substance. It's not like a drug or something. But sometimes they give people, and sometimes it sometimes work. Some people just want to just take something. So that's what we call a placebo. So now AB1, now look at the effect. AB2, look at the effect. AB2, 30 were still sick, and so on and so forth. You can see the whole table. This is a contingency table. Now, when you see a table like this, guys, this is the perfect scenario for test of independence. So if you have in your exam a table like this, just start leaning on test of independence. I told you guys already that chi-square works for categorical data that are fixed in categories like this. They work best for categorical data. So you can see here, this 20 represents this category. Have one seed, that's a category for that. Up to test efficiently, and that's why we always lean to chi-square when we see a scenario like this. Good. Now, this is beautiful. This is an observed value now. They are looking at the effect of AB1, looking at what does this draw. Good. When you want to do this testing now, you know you want to use a test. You want to use the test for independence. So there are a few things I would need to, number one, talk about, because this is different from goodness of fit. So guys, I believe at this point, you guys are still very much with me. Now, don't forget, I'm going to tell you quickly again. I'm sure you guys know this already from your understanding of matrices. We have, for this particular question, now we have 2 rows and we have 3 columns. So because when you want to find your degree of freedom under this test for independence, degree of freedom is given as R minus 1, C minus 1. All right, this is how you find your degree of freedom under test of independence. So you go on to count the number of rows, 1, 2. That means in this case now, we have 2 rows, that will be 2 minus 1. How many columns do we have? We have 3 columns. All right. That will be 3 minus 1. So this will be 1 times 2. So the degree of freedom in this case is 2. So this is how you find the degree of freedom. Note that that's one of the differences between test of independence and goodness of fit. Don't forget, for goodness of fit, the way we found our degree of freedom, which obviously we didn't have a cross classification table in that case. We only had expected and observed. If you remember, it wasn't cross classification. In that case, we always found our degree of freedom by just saying k minus 1, the number of categories we had. But in this case, we check the number of rows, we check the number of columns, and we use this formula: row minus 1, number of row minus 1, the number of column minus 1. That's how we get, we multiply them together, that's how we get our degree of freedom. Good. Now, having done that, the next thing I need to talk about is, obviously, you know that for you to find, the reason why we have to find the degree of freedom, obviously, is for our critical value. I told you guys already that the chi-square distribution is obviously a right-skewed distribution, and I gave you guys a sketch on how it looks like. So for this one where degree of freedom is 2, obviously our table may look more like this. I told you guys already how these things go. I told you degree of freedom of 2, 3. I did for 1 to 5. So obviously you need to just find a way to learn it if you want to, but just remember, it's never a symmetric distribution. It's always a right-skewed distribution. So let's say we have this right-skewed distribution. So you use this degree of freedom to go find the critical value from your table. What we can call it table value, all right? Another name for it is the critical value. The critical value is obviously that thing that it's that thing that separates the critical region from the acceptance region. So you want to find the critical value. That means you want to find at what point are you going to be deciding to, depending on whatever your test analysis gives you, are you going to be deciding to reject the null hypothesis? So what's the critical value? You go on to your table now. Depending on the level of significance, that's your alpha. Whatever alpha they gave you. Now for this question, I believe the alpha given here was 0.05, right? Yeah, I should think so. Okay, no, the alpha was actually 0.1. 0.1. So alpha in this case was given as 0.1. All right. So the way you find a critical value is for you to go on now to check your table. So you go on to check the table, and you, of course, search for degree of freedom of 2 under the chi-square of alpha being 0.1. Can anybody quickly do that right away and tell me what will be the critical value for this particular question? So you go on to check quickly on your table, your chi-square table, what is the value when you had degree of freedom of 2 under the chi-square value of 0.1. Can anybody give me whatever this value will be? If you have a table right there, just so that we can, of course, that's so nobody gets confused. It's still the same process. The only difference is for you to learn how to find the degree of freedom under test of independence, which is different. It's obviously different from that of goodness of fit. You can see the formula right in front: R minus 1, C minus 1. So we have 2 as our degree of freedom and alpha as 0.1. So what is the value for the critical value that you found from your table? Can anybody tell me? Go on to check your table value now. So you have to pull out your chi-square table quickly. Okay, somebody got 4.605. Okay, let me confirm that from my own table. I believe that was correct. That's correct, actually. That's a good answer, but let me confirm it. So I'm going to be checking. Okay, somebody else has also confirmed it, 4.605. So you go on to check alpha being 0.1. So I can see 0.1. Okay, I can see 0.1. Yeah, that's the 1, 2, 3, 4, 5, 6, the 6th column. And I can see 4.605. That's quite nice. So 4.605 was actually what? 4.605 was actually the table value I got. Now, that means your critical value will be 4.605. So obviously, you know that if your test statistics, when you eventually calculate it, falls within this region, you are going to be rejecting the null hypothesis. Now, let me go back to trying to state my null hypothesis based on this question I was given. So we have, of course, our HABs being given, and we want to check if the HABs have an effect on a patient being sick or not sick. So I told you guys already that your HO, your null hypothesis, must always have the context of independence. That means this, there are two things here now. This is patient, like sick, not sick. This is HABs. So you want to find out if this HABs has any dependence, if being sick or not sick is dependent on the HABs use or something like that. You understand the whole thing? If there is dependence, that means the HABs or whatever is here, it may not be HABs. So probably because of the weather. Is anybody there? Okay, it's clear. Okay, good. So as I was saying, we're done with finding the critical value from our table using the degree of freedom and our level of significance, the alpha value. You guys, or some of you told me that the answer you got from your table was 4.605, which I also confirmed. All right. Now, I wanted to, before going into the test statistics, which is a very important thing to explain, I want to quickly try to state the null hypothesis on the basis of this question. Because I told you guys already that this H naught must always reflect this statement: there is independence. So I was trying to explain before the network had an issue. I was trying to explain what is the meaning of this there is independence. It means this side of things. Of course, these questions may differ. But this particular question now is saying this is Habs, then this is the state of individuals using them. Sick, not sick. This is Habs. So our H naught will be saying these two things, there is no dependency between them. That means there is independence. Independence means there is no dependency. Your H naught must always reflect that, meaning that Habs and being sick or not sick has nothing to do with each other. So Habs don't relate to if someone is sick or not sick. There is no dependency. Of course, the HA, the alternative hypothesis, will obviously be saying different. That means you'll be saying there is dependency. That means you can see I said no independence. No independence actually means there is dependency. So your HA will be saying that they do depend. But your HO will say there is independence. Note it. We are testing for independence. So your HA will say there is independence. That means they don't depend on each other. So if I wanted to write this now in this context of this question now, of course, as much as you can, try and avoid writing it this way. As much as you can. Try and avoid writing it as there is independence, there is no independence. You know, try and follow through on what the question said. So based on this question now, if I wanted to state my own hypothesis, as I told you guys already, we may have different words in our null hypothesis, but it must still say the same thing. Your HO must always say there is independence. Independent, that means they don't depend on each other. So a way I may want to frame this now would be that Habs do nothing. I mean, we just say Habs do nothing. That means the Hab you use, since we are saying there is no dependency, there is independence, that means this one and this one don't depend on each other. That means Habs don't do anything. It doesn't affect if somebody being sick or not sick. That's the meaning of that. There's no dependency. There is independence. They don't depend on each other. Independence, that means they don't depend on it. Do you guys understand? No, I don't like to use the word correlation. Correlation is an aspect of, I don't like to use related. That's not nice. Don't use correlation. Correlation, related is different from this. This is not related. This is not about the relationship between them. This is dependence. This is test of independence, saying they don't depend. It's different from relationship. So Habs do nothing is a good way of me saying there is independence. Of course, if I wanted to state my HA, which I said, of course, must say they depend on each other. HA will be saying they depend on each other. So, of course, I can write it as Habs do something. So simple. So make sure you note this. This is very vital. You want to solve a question. Before hasting to solve the test IC and DF and degree of freedom and whatever you want to do, state your hypothesis properly. Make sure, as I said, your H naught must reflect there is independence. Please don't confuse it for each other. There is independence. Just take it from the word test of independence. There is independence. That means they don't depend on each other. That's what HO will say. HA will now say there is no independence. That means there is dependency. If there is no independence, that means there is dependence. That means they do depend on each other. And a way of saying this, look at, based on the question I'm dealing with, you may have different questions. So in this particular question, I can say it this way, that Habs do nothing. So if you like, take AB1 or take AB2 or take like, it doesn't have anything to do with being sick or not sick. Habs do nothing. There is independence. There is no dependency. That's the meaning. So I needed to emphasize on that so that you guys get very good at stating your hypothesis. I told you guys already, testing is still literally the same procedure. The only thing that will be added is all these differences. How do you state hypotheses? How do you calculate degree of freedom? What's the test statistics and so on? But the procedure is still the same. So you see, the first thing I want to do here, after stating my hypothesis, is I want to go on to calculate the degree of freedom so that I can get my tabulated value, which is what we call critical value from my table. So to get my table value, I need my degree of freedom, which is gotten as number of rows minus 1, number of column minus 1. Number of row here, this is row 1, 2. Number of column, this 1, 2, 3. So that's 2 minus 1, 3 minus 1. That means we have, if you multiply them together, we get 2. And we are giving our level of fingers at 0.1. So you go on to your table to check for degree of freedom of 2 under alpha being 0.1. You see all these things are very much clear on your table. You get 4.605. So that's going to be our critical value. Critical value, the critical value is actually that value that will divide that would be the distinction between the rejection region, the critical region, and the acceptance region. So this is it right here. So now this is good. We have been able to draw a diagram. Of course, the diagram we are drawing is because the reason why we're drawing this is not, there's no magic to this. This is not anything difficult. This is just knowing that number one, chi-square is a right skewed distribution. It's not a symmetric distribution. So you have to draw it in a way that it's showing right skewed. Now, I do not know if they're going to penalize you if you don't get the exact way it's supposed to be. I don't think so. But again, this is the reason I'm drawing it like this is because I gave you guys a diagram that showed when your degree of freedom was 1, when it was 2, and so because this one is 2, this is the shape it takes. So, and this is it right here. So the next thing I need to do is to go on now to find my test statistics. So when I'm done getting these test statistics, that's the observed minus expected all square over expected. If I'm done getting that, whatever value I get, I come and check it out here. If it falls in the rejection region, in the critical region, I will obviously be rejecting the null hypothesis. And if it doesn't fall in the rejection region, I will not be rejecting the null hypothesis. It's that simple, no more, no less. Follow this procedure, you can't go wrong. And this applies to literally every form of testing we have been doing so far. All right. So the next thing now is how do we get our test statistics, which is what we have right here. This is it right here. Observed minus expected. Now, how do we get this? This is very, very vital. Very, very vital. Now, this is where I would expect you guys to, even if you have not gotten any other one yet, I would expect you to pay attention to this because this is one of the key to understanding this thing. This is probably one of the biggest changes that is going to come from test of independence. Now, everything you have right here is what we classify as the observed value. Note that this is actually the observed value. So it was observed that more like one other way we can say it's more like the sample value, the sample we conducted. This is what we got. We got that 20 represented AB1 and SIC and every other thing. This is the observed value. But the question is, how do we get the expected value? How do we get the expected value? Very, very simple, but you need to pay attention. Okay, so let's leave this right here. This is what's going to give us the final decision. All right, this is what we're going to use to find the final decision. But we want to now go on to find our test statistics, which of course you can see right here in our test statistics. This is observed minus expected. Observed is already gotten. This is all the observed value. But what's our expected value? What's our expected value? How do we get the expected value? So guys, please, I really need your attention at this point. This is how you get your expected value. You're going to have to do something. You're going to have to find the total of each categories, meaning that you want to make a total of each category. So I'm going to be making a total of this. Total of this obviously will be 120. That's 20 plus 100. The total of this will be 140. That's 30 plus 110. And the total of this will be what? 120. You can see that it's that easy. I believe everybody can do that. So you do all that's for you've done the total for each of the columns. Column 1 now, the total for column 1 was 120, total for column 2 was 140, total for column 3 was 120. All right. Now, you now need to do the total of the row also. So this row 1. This row 1. So you go on to solve 20 plus 30 plus 30. That's 60 plus 20. That will give you 80. All right. 20 plus 30 plus 30. That'll give you 80. So you just go on to find the total of each of the rows and column. 100 plus 110 plus 90, that will give you 300. I'm sure that's easy for everyone to do. It's just addition. Now, one, if you have done the right additions or no, is that when you sum these two total for the row, the value you get must be the same value you got when you sum the three total for the column. So you go on now to do 120 plus 140 plus 120. This obviously is 260, 380. So from my column, the total for this column, I got 380. You check 80 plus 300 is also 380. Obviously, we have done everything right in this case. Good. So again, don't forget what we are trying to do here. We're trying to find the expected value. We have gotten the observed value. The observed value is what we were given before. The expected value is the way to find expected value is what I'm trying to explain here. So now please pay attention. Please pay attention. Each of the expected value, don't forget, these are the entries we had. All these are just the columns. Sorry, are just the total. This is the major entry, 20, 30, 30, 100, 110, 90. These are the observed values. You have 6 of them. All right, you can see them. 6 of them. 1, 2, 3, 4, 5, 6. Now, what we want to find here is the expected value for each of them. The expected value for this one, that means when observed was 20, what was the expected value? We also want to find the observed value, the expected value when the observed value was 30. What was the expected value here? For this 130 also, what's the expected value? For this one, what's the expected value? For this 110, what's the expected value? For 90, what's the expected value? That's what we want to find, because it's from there we'll be able to find our test statistics that says observed minus expected over. So we have to do for each of them, then sum them all together. That's going to be what our test statistics will be. So we have to go on to find the expected value for each of these entries. All right. So this is what you're going to do. Note the expected value will be like this. I'm going to just say this way. Of course, just to make it less complex. Please, can anybody indicate if you can still hear me, please? Hopefully the network is not. Can anybody still hear me? Am I communicating with anybody? Please confirm if you can hear me, please. Is it clear? Like, you can hear me clearly, everything is clear, there's no issue. Can you please confirm, because I want to move on. I want to be sure that you guys are following. Okay. 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 All right. Okay. All right. So look at what's going on right here now. I want to find the expected value for when the observed value was 20 and for every other one. All right. This is how you find it. This is the formula for finding the expected value of each of these entries. We have 6 entries here: 20, 30, 30, 100, 110, 90. These are the observed values that we have. We want to find their respective expected value. This is the formula you're going to use. You're going to be using row total multiplied by column total over total. What I really mean here by total is the entire total. So now look at what we're going to do right here. If I want to find for 20, the entry 20, the entry of 20, 20 is on row 1. What's the total on row 1? 80. So I'm going to be writing 80 multiplied by 20. This entry 20 is on what column? Column 1. You can see the column right here. What's the total under this column 1? 120. Now, what's the entire total? The entire total is 380. It is this calculation that will give you the expected value for the entry 20. So if you press this on a calculator, 80 times 120 over 380. What does it give you? Can anybody give me the answer to that? You get the value of, I believe, 25.3. 25.3 thereby will be representing the expected value. The expected value for the entry 20. So the expected value here will be 25.3. So I'll be writing them close to each other so you can see. So this is the expected value as calculated now. Good. Let's try and find for another one. Let's find for 100. How do we find the expected value for this value 100? Of course, you follow this formula again. Row total, what's this row 2 right here? What's the total for row 2? It was 300. So you go on to find this as 300 multiplied by, what's the column total? This 100 was on column 1 with a total of 120. So 120 divided by 380. So for this 100, we're going to be finding the expected value as the row total, which was 300, multiplied by the column total, which is 120 over the total, 380. So in this case now, if you put this on a calculator, what value is it going to be giving you? I believe you should get 94.7. You can confirm that. Okay, so 94.7. Good. Now, you can go on now without wasting time to find for the rest. So for that of 30, for me to find the expected value for 30, I go to the row total here. Row total here is 80. 80. And I go on to the column total. Column total is 140. That will be 80 multiplied by 140 divided by 380. So you tell me what you got there when you put this on the calculator. I believe you got 29.4. All right. So you do for the rest. Look at that of 110. Of course, for 110, you would have 300 multiplied by 140. Okay, this is 29.5. So what's 300 multiplied by 140 over 300? Can you do it for the next one? So this is how you're going to be finding the expected value for every entry in the contingency table. Okay, so 110.5. So this is going to be 29.5, 5 not 4, and this is 110.5. So if you do for the remaining two, this should be 25.3. And the one you have next should be 94.7. All right, so that is going to be for that's going to be all for the entries. The 6 different entries we have right here, we've gotten their expected value. Now, let me give you something that must happen, that you must notice. When you're done with these expected values, if you do 25.3 plus 94.7, the value you get when you add these two together must be the total here also. So you can see that 25.3 plus 94.7 is still 120, all right? 29.5 plus 110.5 is still 140. You can see it goes on and on. The same thing goes for the row. So let's move on now. I actually felt this was supposed to be 29.4 and this one was supposed to be 110.6. But anyway, probably that's not a very big deal. The network seems to be making the video blur. I do not know why. I think the network is not able to pull through on getting the video. Is it still? How far? How do you guys feel now? Is it better in terms of the blurry? In terms of it being blurry, is it better? Still blur? Is it better? Okay, it's better a bit. Okay. All right. So now that we are done with getting this expected value, it's time for us to now calculate our test statistics, which is the basis of everything we've been doing. Now look at what's going on here. We've gotten expected value of each of the entries. So what we can do now is simply go on now to say, for the first entry of 20, I would have it this way. That will be 20. I'm trying to find the test statistics already. That will be 20 minus 25.3, which was the expected value, all square over, of course, expected value 25.3. Plus, I go to the next one. Whichever one you want to take, then let me take this next. 30, the observed, minus the expected 29.5, all square over 29.5, plus the next entry, 30 minus 25.3, all square over 25.3. So you keep doing this till you're done with all the entries. All right. So you will do for each of the entries and find a final value. And that final value is what will be your test statistics. So I don't know if you guys can quickly drop this in a calculator. Of course, you can easily do that by using, if you're using a scientific calculator, the 20 minus 25.3 all square over, just open a fraction and then add it with each and every one of them and press everything once. So what did you get as your final answer? Anybody yet? So can you press all this on the calculator and tell me what the final answer will be? All right. Network is quite not very good today. And apologies for that. We don't have so much power over that, but we're just trying our best right here. So I hope you guys can hear me. Hope you guys can hear me. So based on what we're solving, you can see that after pressing all this in the calculator, we were able to get 2.53, I guess, as the test statistics. All right. So just like every other thing we've been doing, every other testing, we got our test statistics to be 2.53. We had our critical value to be 4.06. Obviously, this is our critical region, our rejection region, and this is our acceptance region. So we need to go on to investigate, does 2.53 falls inside the rejection or acceptance region? All right. Obviously, you can see that 2.53 it cannot fall inside the rejection region. So obviously, it falls outside the rejection region, meaning that we do not reject the null hypothesis because it's not in the rejection region. So our conclusion would be that we cannot reject the null hypothesis. So that means we are not going to be rejecting null hypothesis. Obviously, meaning we're going to be accepting null hypothesis. So that's just it. All right, that's just it. So this is the whole idea around contingency table. I'm not very sure we will be able to continue this class at this time. I would advise you go through this video once it's released. We have more questions. You have more questions in your notes. You can use that to solidify your knowledge. So it's very simple. Probably I do a quick recap. Number one, stating your null hypothesis and your alternative hypothesis. Make sure your null hypothesis always indicates there is independence. There is independence. If you hear the word independence, meaning there is, when they say there is independence, that means there is no dependency. Note the difference. Don't get that as the meaning of independence means there is no dependency. So what are you looking for dependency on? That means you are looking at the two ways. You know that this is a two-way table. So the row and the column, whatever is contained in your column doesn't depend on that of the row. That's what you are saying there. That there is no dependence. That means they don't depend on each other. Good. Now, the other thing is, how do you find your critical value? You find your critical value by getting the degree of freedom. How do you get your degree of freedom? You do the row minus 1. Number of rows. In this case, we have 2 rows. And we have how many columns? You have 3 columns. So you do row minus 1, multiply by column minus 1. You get your degree of freedom there. You check it on your table, you find your critical value. Good. Of course, this is perfect. After you have done this, then the next thing is for you to go find your test statistics so that you'll be able to check the result and see if it did fall inside the critical region or no. So if it falls in the critical region, the rejection region, obviously you're going to be rejecting null hypothesis. Now, to find your test statistics, The biggest issue here is that even though the values you'll be given will be the observed value, but you don't know your expected value. So that's why you have to go use this formula right here. Of course, the first thing you want to do is to make a total of all the columns and total of all the rows. You can see what we did here. We added 20 plus 100, 120, 30 plus, 140, 30 plus 90, 120. We did for the row, 20 plus 30 plus 30, 80, and we did for the second row. We got the total for both and the total for the 3 columns. Now, following this formula, for us to get the expected value of each of the entries, that for 20 right now, we will say, what's the row total? This is 20 is on row 1. What's the row total there? That's 80. That'll be 80 multiplied by, what's the column total? 120. 120 divided by, what's the total? 380. That's how we're going to get, we got 25.3 there. We do the same thing for all the entries. You get the respective expected value for each and every one of them. Having done that, then you can now use the values you've gotten to fix into the test statistics, the observed minus expected all square over expected. Sum everything, get a value. I told you guys what these test statistics represent. I've told you guys at the beginning of our introduction to significant testing. It's a very important value. It's a value that actually decides everything. So we got 2.53. So we come to our curve right here, and we can see that 2.53, we want to check if it falls in the rejection region or not. And we saw that 2.53 obviously doesn't fall in the rejection region. So obviously we're going to be concluding that we cannot reject the null hypothesis. All right, so we are doing this at a alpha being 0.1. Don't forget, our alpha was 0.1. So guys, that's just everything. It's quite very simple. So when this video is out, guys, make sure you go through it well. We have more questions, and I expect you to get this thoroughly. So thank you guys for really joining. I wish you guys the best. Enjoy the night. Enjoy the weather. Sleep well. I wish you the best in the exam coming up.